I've really been neglecting FMA too much. I haven't done FMA for like the past 4 months. I really can't do this. It's coming up so fast. We gotta do something. Hello everybody, I'm Kara, and today we're gonna stop neglecting FMA because one of you guys recommended that I do 75 minutes of solving FMA problems. So today we're gonna do exactly that because 75 minutes for 75 subscribers. Thank you guys so much. It means so much to me that you guys are actually watching my videos, like the videos. Thank you guys so much. But enough talking about me. We're gonna talk about FMA problems. Alright, this is perfect because in a normal FMA contest you get 75 minutes, 25 questions. So basically I'm just going to be going through the 2008 FMA contest and explaining my problem solving strategy. I think this would be kind of boring if I show you guys the whole 75 minutes, so I'll cut out all the uneducational parts and hopefully this should be educational. Let's see. Alright, let's start our timer and let's get into it. Alright, we're going down. Number 1, a bird flying in a straight line initially at 10 meters per second uniformly increases its speed to 18 while covering it. Alright, just a big 5 random thing. Alright, so we got V0. Oh, we got VF and V. Alright, so we got VF and V initial, so it's just 18 squared minus 10 squared is equal to 2AD, which is 40. And then we just divide this and we get A is approximately what? Let's use a calculator. So the answer is A is approximately equal to 2.8 meters per second squared. And our answer is just D. Alright, I'm just going to record all my answers on this paper over here just so that we can check at the end. Alright, so 1, we got D. Alright, number 2, a cockroach is crawling along the walls inside a cubicle room that has edge on 3. If the cockroach starts in the back lower left hand corner of the cube and finishes at the upper right hand corner, what is the magnitude of displacement? Alright, so we just have a cube. And then it goes from this corner to this corner, and then we just have to find the space diagonal. Alright, so that's just root 3. So 3 root 3 should be the answer. This is just something you should memorize, right? Like in a cube, the space diagonal is root 3 times the side length. So it's C. By the way, this is a pretty epic calculator, TI-36X. It can solve polynomials, and it's a scientific calculator, and it's pretty epic. So you guys should get this calculator if you are thinking about what scientific calculator to get. Alright, number 3. Position versus time for an object moving in a straight line is shown below. What is the instantaneous velocity at t equals 2 seconds? That's just the slope of the position versus time graph, and it's quite clearly the same everywhere. So this is obviously like the slope of the position versus time graph, so we can just do the delta y over delta x, and we know that's negative 4 over 2, which is just negative 2. And our answer is just A. Alright, number 4. Alright, what's the maximum displacement from the start for the toy car? So basically, if you're given a velocity versus time graph, the displacement is just the area under the curve, and we know that it's probably going to be at this time over here, because over here the area is positive, but once you get over here the area is negative. So basically we want to find the maximum, so we just take the area under this, and let us see, this is a trapezoid plus a rectangle plus a triangle. So we got a trapezoid, we got a rectangle, and then we got a triangle. I could draw, this is a beautiful drawing. What are you talking about? Okay, so we have a 2, and then this goes to 4, and then 4, and then this length over here is 2. No, it's just 1. And then this width of this is 0.5, and then the width of this is 1. And then we just find the area of this, which shouldn't be too hard. It's 3 for the trapezoid times 1 for the trapezoid plus 4 times 0.5 for the rectangle, and then plus 4 times 1 over 2 for the triangle. And then this is just equal to, let's do it in our calculator, this is just 7. So our displacement would be 7 meters. The answer is D. Let's go. Number 5. Which of the following acceleration versus time graphs most closely represents the acceleration of the toy car? So it's the same velocity versus time graph. So in a velocity versus time graph, the acceleration is just the slope of that. So basically the slope is positive here, right? Constant and positive, then it goes to 0, and then it's constant and negative. So, and also the negative magnitude of acceleration, because the slope is steeper, is greater. So it's probably this one over here. See? Positive acceleration, constant, 0 acceleration, and constant, and then a bigger negative acceleration and constant. So the answer is just C. Number 6. A cannon fires projectiles on a flat range at a fixed speed but with variable angle. The maximum range of the cannon is L. What is the range of the cannon when it fires at an angle of pi over 6 above the horizontal? So basically a really good thing to remember when you're doing this kind of problem is that the maximum range is at pi over 4. So basically if you do it out using kinematics, you get that the range is just v0 squared sine 2 theta over g. Now, I know this is not completely obvious directly, but this is a formula you should remember because projectile motion comes up a lot in FMA. So basically what it's saying is that the maximum is when sine 2 theta equals 1. So it's basically saying that v0 squared over g is equal to L. And then we want to find what it is when theta is equal to pi over 6. So if we plug in pi over 6 to this thing, we get v0 squared times sine of pi over 3, which is just root 3 over 2, and then over g, and then v0 squared over g we know is L, so just L root 3 over 2. Alright, the answer then is A. A toboggan sled is traveling 2 meters per second across the snow. The sled and its riders have a combined mass of 120 kilograms. Another child, m equals 40 kg, headed in the opposite direction, jumps on the sled from the front. She has a speed of 5 meters per second immediately before she lands on the sled. What is the new speed of the sled? Neglect any effects of friction. Alright, so this just seems like a momentum kind of thing, because you have a toboggan, then you jump on, then it should have constant momentum. Alright, let's draw this. So we have a toboggan, and then we have 2 meters per second, and this whole thing is 120 kg. And then another child over here jumps on the sled from the front. So she's 40 kilograms, and then she's going this way at 5 meters per second. So basically what this is an inelastic collision, right? Because the girl jumps on and then they stick together because they're all stuck on the sled. So basically, in an inelastic collision, you basically say that 120 times 2, which is the momentum in this direction, well, I mean, the direction of the sled is 120 times 2, that's the momentum in that direction. And then the momentum in the opposite direction is 40 times 5, mv. And then this is just equal to the total mass, which is 160 after they stick together, times the final velocity. So we just plug this into our calculator and we get v is approximately what? Let's see. So then we just get that v is approximately 0.25 meters per second, which is A again. Too many A's, this is sketchy. Alright, moving on. Number 8. How much time do we have? Very epic. So we only spent like 15 minutes on the first 7. We're gonna keep going. Number 8. Riders in a carnival ride stand with their backs against the wall of a circular room of diameter 8 meters. The room is spinning horizontally about an axis through its center with a rate of 45 revs per minute when the floor drops so that it no longer provides any support for the riders. What is the minimum coefficient of static friction between the wall and the rider required so that the rider does not slide down the wall? That was a long question. Okay, let's do this. Alright, so we have a room, okay, and then there's a guy over here. And then basically, he has some normal force on him, pushing towards the center of the thing, and then that's the only, and then there's a friction force pushing him up, and then there's gravity pushing him down. So basically we want the friction force to equal his gravity, but first we have to find what his normal force is on him. So the normal force is just equal to the centripetal force. So the way you calculate centripetal force is mv squared over r, and then we know that v is equal to rw, and w in this case is 45 rev per minute. So we first convert this to radians, right? So 45 times 2 pi over 60, because we want to find it in radians per second. Alright, so we get that it's just 4.7 radians per second. And then that means that v is just equal to, well, we don't even have to find v. We know that this is also equal to mrw squared. So we could just plug everything in. We could get the centripetal force is approximately, let's see. So mass is what? Oh, I think mass will cancel out. Wait, let us write the full equation. So we have that our centripetal acceleration times the coefficient of static friction is our friction force, and then that's equal to our mg. So we have that mg is equal to mrw squared mu. Alright, so m cancels out, and then we just have that mu is equal to g over rw squared. And we get, and then we just plug everything in. Epic! 9 point, wait, are we supposed to, I'm pretty sure we assume d equals 10, but let's make sure for this one. Yeah, d equals 10, okay. So 10 over the radius, which is 8, oh no, shoot. Diameter, do not mess this up on the actual alphabet. Diameter is 8, so divide by 4, and then divide by 4.7 squared. And then we get 0.11, which is answer C. Hurry, no more A's. Okay, 9. A ball of mass m1 travels along the x-axis in the positive direction with a speed of v0. It then collides with a ball of mass 2 that is originally at rest. After the collision, the ball of mass m1 has a velocity of blah 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 blah. Consider the following 5 statements. Okay. So it's traveling along the x-axis. Oh wait, there multiple can be right. Okay, let's just go through it, right? Alright, so number 1, m1 v1x plus m1 v2x. Okay, that's just straight up wrong, right? Because you never multiply m1 by v2x because v2x is on m2. It has nothing to do with m1, so that's just wrong. Alright, m1 v0 is equal to, okay, so v0 is in the x direction. So the final y velocities have nothing to do with the x direction. So this one's obviously wrong too. And then m1 v1y plus m2 v2y equals 0, which makes sense, right? When the ball is just traveling in the x direction, it has no y momentum, right? So that means that at the end, it can't have any y momentum, so that means the momentums have to sum to 0 in the y direction. Okay, so 3 is right. That's pretty epic. Okay, and then m1 v0 equals this. Alright, this, no. We need m2 in here somewhere, so this is just straight up wrong. And then 5 is the same thing, except it does have m2. So this is the conservation momentum in the x direction, which is perfect. So 3 and 5, 3 and 5, wait, 3 and 5, yeah, 3 and 5, okay. That took me a while to find, dang. B. Alright, 10. An experiment consisting of pulling a heavy wooden block across a level surface with a spring force meter? Oh, spring force meter, okay. The constant force for each try is recorded, as is the acceleration of the block. So basically, we know that the very title of this competition is F equals ma. So we're done. No, I'm kidding. Okay, so basically, what we could do is we could just divide each of the forces by m to get our acceleration for each trial, and then just average them. Wait a minute, is there friction or wait? Alright, let's try this and see what happens. Alright, so for the first one we get 32, then for the second one, what do we get? We get 17? Okay, so there must be friction somewhere. Okay, wait, let's try this again. Okay, there's for sure friction because these are not equal. So, basically we have our block, we have F this way, and we have friction the other way. So basically, we have, instead of F equals ma, we have F minus small f equals ma. So now we could just plug in for 2 of these equations with 2 of the trials, and then we should have a system of equations to solve. So let's do this. Alright, so the first trial we have 3.05 minus small f is equal to m times 0.095. And then for the second trial we have 3.45 minus f is equal to m times 0.205. And then if we just subtract these, if we just subtract the first one from the second one, then we get rid of the f, and then we can solve for m. So we get m is equal to 3.45 minus 3.05 over 0.205 minus 0.095, which is approximately what? Alright, so we get that the mass is about 3.6, which is the closest to A. Alright, let's try that. So 10 is A, but I am not convinced. I feel like we did something wrong. So let us just check with a different try. Let's try 4.05 over here. And then the acceleration would be 0.295. Okay, so this would be 0.295 and 4.05. And that gives us 5. Hold up. This is not ideal, huh? Well, if we get different answers, then it's kind of troll. Alright, let's try a different one. Alright, I got 4.5 for a different one, and then... So it's either A or B. So I think that it's closer to B, but let's just try it with one more. Alright, yeah, so it's closer to 5. So I think that most of them give us 5. So we'll just do with B. Alright, what are the best coefficient of friction between the two? So we could just plug in m equals 5 and then solve for f over here. So let's see, 0.095 times 5 and then minus 3.05 is equal to 2.5, and then that gives us that f is equal to 2.6, and that, so f is equal to 2.6, and then we have to divide by mg. So divided by 5, divided by 9.81, and we get 0.05. So I think A is the right answer for this case. Let us try with a different value actually, real quick. Okay, yeah, it's around 0.05, so this should be good. Alright, moving on. Number 12. How much time do we have? Alright, we're kind of cutting it close. We need to go faster. So 12. A uniform disk rotates at a fixed angular velocity on an axis through its center normal to the plane of the disk and has kinetic energy E. If the same disk rotates at the same angular velocity about an axis on the edge of the disk, what is its kinetic energy? Alright. So basically, for this, you basically know that kinetic energy is equal to 1/2 I W squared. And by the parallel axis theorem, if you have something and it's spinning through its axis, right, like that, if you move the axis r away from the center of mass, if this is r, then you get the center of mass, ICM, plus mr squared is equal to I prime. So basically for the initial kinetic energy, we have that the I for a uniform disk is just 1/2 mr squared. So we have 1/2 times 1/2 mr squared times w squared. And this is just equal to E, right? Because E is our initial kinetic energy. But then to get our final kinetic energy, we have to replace our 1/2 mr squared with this over here, our I prime. So we just add mr squared to that, so we get 3/2 mr squared instead. So that's just 3 times our initial kinetic energy, which is D. Let me just explain that real quick. So you have 3/2 over here, and then to get from 1/2 to 3/2, you just multiply by 3 over here. So yeah. Alright, number 13. A mass is attached to the wall by a spring of constant K. When the spring is at its natural length, the mass is given a certain initial velocity, resulting in oscillations, right, that's so hard to say, of amplitude A, as the spring is replaced by a spring constant of 2K, and the mass is given the same initial velocity. What is the amplitude of the resulting oscillation? So basically we have a spring, and then we have a mass, and it's all on the ground, and we have K over here, and the initial amplitude is A. So basically it's asking if we have that this was 2K, how far would the amplitude be? So let's first find the amplitude in terms of K. So basically the way to find amplitude is the maximum extent at which the spring goes, right? So that's just equal to its potential energy at the very end, because at the very end it has no kinetic energy, so that's just the maximum energy in the system. So at the equilibrium position, when it's pushed with the initial velocity, it has no potential energy, okay? But it has kinetic energy. So it starts with this much energy. This is its total energy, and then at the end it ends with pure potential energy. So that's just represented by 1/2 kx squared, but in this case it's just a squared. So basically we know that m and v are constant, but k is what changes. So initially our amplitude is just this, but after you change k to 2k, you have to divide a by root 2. So we just get the answer is B. 14. A spaceborne energy storage device consists of 2 equal masses connected by a tether and rotating about the center of mass. Additional energy is stored by reeling in the tether. No external forces are applied. Bro, this is so hard to read. Initially, the device has kinetic energy E and rotates at an angular velocity omega. Energy is added until the device rotates at an angular velocity 2 omega. What is the new kinetic energy of the device? Alright, let us erase this. Alright, so we basically have 2 equal masses, right? So we have this one over here, we have a center of mass, and then we have another one over here, and they're going like that. So basically the kinetic energy we know is 1/2 I w squared, right? And if you have 2 masses, each a distance r away, then I is just equal to 2 mr squared. Alright, so we have our initial kinetic energy, right? Oh, okay, so two things change right now. Not only does the angular velocity change, but also the r has to change, because it says that it reels in the tether. So in order to relate r and w, we have to use another equation, which is angular momentum. So basically you learned that angular momentum is conserved, and angular momentum is just IW is equal to I prime W prime. So basically 2 mr squared W is equal to 2 mr prime squared times W prime, which we know is just 2W, so we can just replace this with 2W. And then if we divide everything out, we just get that r prime over r is equal to 1 over root 2. So now we can plug everything into our initial equation, right? So this is our initial moment of inertia. So this is our initial energy, right, over here. So if we want to find our final kinetic energy, we just do 1/2 I prime W prime squared, which is equal to 1/2 times 2m r prime squared, which is just r over root 2, and then times 2w squared. And this is just equal to 1/2 times 2m r squared times 4 over root 2 squared, 4 over 2 w squared, and then we just get that our final is just, and then this is just equal to 4 times 1/2 times 2m r squared w squared, which is 4 times our initial kinetic energy. So the answer is just D. Alright, that was a pretty intense problem. Okay, moving on. 15. How much time do we have? Alright, 30 minutes on the first 15, 14 is not bad at all. Okay, a uniform round tabletop of diameter 4.0 meters and mass 50 kilograms rests on a massless, evenly spaced legs of 1 and spacing 3. A carpenter sits on an edge of the table. What is the maximum mass of the carpenter such that the table remains upright? Alright, this is just a torque problem. So let us just look at the tabletop and look at the torque on that. Alright, so basically the tabletop's flat, right? And we first have one force from the support, so F1. We have the weight of the table is at the center of mass, mg. And then we have another force over here from the other support. And then we have the downward force of the carpenter, which is m. We get to say, does we have the carpenter's mass? We don't have the carpenter's mass, so we get to say force of carpenter. Alright, and then we basically want to say that all of these torques cancel out. So what values do we know? The only ones that we don't know are F1 and F2. So we want to get rid of one of those. So basically the table's trying to tip over this way, right? So the right support is always going to be pushing up, but the left support, like at the moment that the table is about to tip over, the left support is not pulling down on it or pulling up on it or anything. That's the point at which it tips over. So basically, to find the maximum force that the carpenter exerts on the table, we just set F1 to equal 0 and then see what the other forces have to be equal to. Well, another way to think about it is like when it's tipping over, F1, the left support of the table, is barely on the ground, so there's no force on the left support. So we just get rid of this, then we only have one unknown. So if we want to get rid of an unknown with torque, all you do is set the pivot point to there. So the torque due to F2 is 0, then this distance is this distance is 1.5, and then this distance over here is 0.5. So we just have that FC times 0.5 is equal to 1.5 mg. And then we get FC is what? Oh, it's asking for the maximum mass. So we have that mg, because the force that the carpenter exerts is just his weight, his mass times the gravity. So mg equals 3 m table g. Okay, so now we just solve for this. 3 times mass of the table is 150. Okay, that's just already there. So 15 is D. Number 16, a massive spring with spring constant K is vertically mounted so that the bottom end is firmly attached to the ground and the top end free. A ball with mass M falls vertically down on the top end of the spring, becoming attached so that the ball oscillates vertically on the spring. What equation describes the acceleration of the ball when it's a height y above the original position of the top end of the spring? But what speed does the ball fall in the spring? Wait, let's clear this. Oh, wait, we don't even need that. We just have to find the net force on the ball, right? Okay, so we have a ball, and then we have a spring, and then basically the forces on the ball are mg, and then mg, and then the spring is also trying to pull it down because it's above the original position of the spring, right? So it's trying to pull the mass down, so that's kx, or ky. So basically the net force on the ball is just mg plus ky, and then that's just equal to ma, yeah. And then if we divide by m, we just get d plus ky over m. But down is negative. Okay, so the force is downwards, so that means our acceleration is negative, so it's just a negative of this, which is on there. So it's E. Alrighty, 17. We're zooming through this. This is epic. A mass M is resting at equilibrium suspended from a vertical spring of natural length L and a spring constant K inside the box as shown. So the box starts accelerating upward with acceleration A. How much closer does the equilibrium position of the mass move to the bottom of the box? Alright, so when you're dealing with accelerated reference frames, what you have to do is you have to add a fictitious force inside. So you know like how like when a car turns, it feels like you're going that way? It's not because you're actually going that way, it's because your car that you're in is actually accelerating to the left. So basically, if you have a box in a thing that's accelerating upwards, you add a force in the opposite direction. So let me draw it out. So like in a normal reference frame, it's just going to be mg, right? But because our reference frame is accelerating upwards, we have to add an opposite force on the block that's going downwards. So we add the downward force, and this is just equal to ma. Alright, so now we have this, and then we have kx, right? And we want all these three forces to be balanced. So originally, the only forces are mg and kx, but once you start accelerating, you add in the ma. So our original equation would be kx is equal to mg. So then we get x is equal to mg over k. But then our x becomes m times g plus a over k. So if we want to find the difference between these two, we just subtract it out and we get what? ma over k. And that is just E. Alright, moving on to number 18. A uniform circular ring of radius r is fixed in place. A particle is placed on the axis of the ring at a distance much greater than r and allowed to fall towards the ring under the influence of the ring's gravity. The particle achieves a maximum speed of v. This ring is replaced with one of the same linear mass density with radius 2r, and the experiment is repeated. What is the new maximum speed of the particle? Alright, so basically, let's draw this. Wait, how much time do we have left? Okay, we have 35 minutes. I think we're pretty safe. Alright, so we have our ring, and then we have a ball that goes over here and goes here. And basically we know that its maximum speed is going to be right when it's over here, because once it gets there, the ring's going to start pulling it backwards. So it starts going faster, and then the ring starts pulling it backwards, and so it slows down. So at the very point where it's in the middle of the ring, it's going to be fastest. So basically, when the ball is really far away from the ring, it has 0 potential energy. But when it gets to the center, we find the potential energy there, and then we could find V. So the formula for potential energy between like two masses is just negative g mm over r. But in this case, we don't have two like point masses, we have one point mass and we have a circle. So basically for every point on the circle, it's going to have this potential energy with the ball. But the circle has a circumference of 2 pi r, so we just consider it to have 2 pi r point masses. So if we want to find the total potential energy, we just multiply by 2 pi r. So basically, like, the r's cancel out, so it doesn't even depend on r. So all we gotta say is that it doesn't depend on r, so it doesn't matter. So the answer is just C. Alright, 19. A car has an engine which delivers constant power. It accelerates from rest at time t0 and at time t equals t0. Wait, what? Oh, at time t equals 0, it's at rest, and at time t0, its acceleration is a0. What is the acceleration at t equals 2t0? Alright, so now we gotta use our power formulas. So, how do we use power formulas? Could you please tell me? I'm stuck. No, I'm kidding. Okay, so power is just force times velocity, basically. So we have that P equals Fv. So that means that A is equal to Fv over m, and we know that power is constant, right? No, sorry. Alright, so we know that acceleration is equal to F over m, which is basically equal to P over Vm. So now what's annoying is that we have acceleration in terms of velocity, but acceleration affects velocity, so this is kind of hard to do. So I'm trying to think of whether there's a way to do this without calculus. Let's see. Oh, well, there's another way we could do it without using calculus. So basically, another thing you could say about power is that it's equal to work over time. So if this is constant, that means that the work done is just equal to power times t is equal to work. And work is just a change in kinetic energy. So that means that pt0 is equal to 1/2 mv squared, v0 squared. But we can still use our other equation, a equals f over m is equal to p over vm. So let's keep that in mind. And then at 2t0, we multiply this equation by 2, and we get that 2pt0 is equal to 1/2 times 2 mv0 squared. And now we want to find out how this relates time to velocity. So we know that we have 2t0 on the left side. So now we have to put this 2 into the v0. So this is the same thing as writing p times 2t0 is equal to 1/2 m times root 2 v0 squared. So basically at time 2t0, our velocity is now root 2 v0. So basically in our acceleration equation, our initial acceleration, our a0, is equal to p over v0m. P and m are constant, so if we look at our final acceleration, af, this is just equal to p over root 2 v0m. So if we relate a0 to af is just a0 over root 2. So the answer is just B. Alrighty. How much time? So we have 30 minutes to do 5 problems. Shouldn't be too bad. Oh no, Young's modulus. I have not reviewed this in a while. We're gonna get through this, I swear. I bet we could do Young's modulus. It can't be that hard. Alright, the Young's modulus E of a material measures how stiff it is. Okay, so it tells us what it is. The larger the value of E, the more stiff the material. Consider a solid rectangular steel beam which is anchored horizontally to a wall at one end. Okay, let's draw this. So it's anchored to a wall at one end and is allowed to deflect under its own weight, so it's like curving down, I guess. The beam has length L, vertical thickness H, with W, mass density P, rho, and Young modulus E. The acceleration due to gravity is d. What is the distance through which the other end moves? Alright, so all of them are dimensionally correct, so we can't troll with dimensionality. So we had to basically see what each variable does. So if it's thicker, it makes sense that it would, it'll move less, right? Okay, so h should be in the denominator. If it's wider, so width so width's like how deep it is from us. So basically, I think that I feel like that would increase the amount it moved, because that means it'd be heavier, so that means it'll like fall down more. And then L for sure makes it move through more, because it's longer, it just like tilts down at the end. Okay, so W and L are in the numerator. Wait, let's write this down. So W and L are in the numerator, H is in the denominator, and then rho. So if it's more dense, that means it'll be heavier at the end, which means it'll have more torque, which means it's harder to move. So I think that if you have more mass density, it's going to fall more. So rho also is in the numerator. And then E. Well, E, if it's more hard, it's for sure not going to move as much. So we can put E in the denominator. Does this match anything? Oh, wait. Does it? Oh, so W is not in any of these. Okay, so it doesn't even depend on it. So the only one that matches our prediction is D, so I'm going to stick with D. Consider a particle at rest which may decay into 2 daughter particles or into 3 daughter particles. What is true in the 2-body case but false in the 3-body case? Alright, let's just go through this then. The velocity vectors of the daughter particles must lie in a single plane. Alright, let's see. So it has to be false in the 3-body case, but I don't think that is true. I don't think that is false in the 3-body case. So basically, let's say one particle goes out this way, then one particle goes out that way, but the third one has to lie in the same plane, otherwise it won't fully cancel out the other two. Because, like, if you think about it, like, let's say this is like a plane, right? Oh, don't want to go all the way back, right? So we have a plane, right? Let's say that this plane is defined by these two vectors. Both these two vectors lie in the plane. We don't know about the third one yet. But if these two lie in the plane, that means that some of them must also lie in the plane. But we know that the third vector is just the opposite of that vector. It's just the opposite of the sum of the previous two vectors. So if the sum lies in the plane, then the third one must lie in the plane, so it's also true for a 3-body case, so A is not right. Alright, given the total kinetic energy of the system and mass of each daughter particle, it is possible to determine the speed of each daughter particle. Well, that's not necessarily true, right? Because, oh wait, speed though. Speed. Well, it's for sure possible in the 2D case because like conservation of momentum and stuff. I feel like it's also true in the 3-body case. Let's see if there's any other obvious ones. Okay. Given the speeds of all but one daughter particle, it is possible to determine the speed of the remaining particle. Okay, hey, perfect. So we don't even have to do anything because this is not true. Because let's say we know that one of the daughter particles goes this way and the other, has speed s1 and the other daughter particle has speed s2. But it depends on what angle this is over here. This theta matters because the sum of the two vectors is what equals the third vector. So if they're like completely opposite, then like the third vector has no speed. But if the theta is really small, then the third speed has to be really big to cancel out because they're both in one direction, so the other one has to go super far in the other direction. So this is false in the 3-body case. Let's show you that it's true in the 2-body case. So in the 2-body case, it just goes like this, right? But then we know for a fact, like immediately, that the other particle has to go at the same speed in the opposite direction. So we know the speed of the other particle. Wait, do we know the masses though? Okay, we kind of had to know the masses though. Unfortunate. This is not good. Now we actually have to do stuff. Okay, so D is true for both cases for sure. C is like not true in either case because we don't know the masses. So is it B or E? That is the question. Okay, do we have enough time to worry about this right now? Okay, I feel like it's a waste of time to, Alright, let's just come back to it. Okay, a bullet of mass M strikes a pendulum of mass M2 suspended from a pivot by a string of length L with horizontal velocity V0. The collision is perfectly inelastic and the bullet sticks to the bob. Find the minimum velocity V0 such that the bob with the bullet inside completes a circular vertical loop. Okay, so this is a fairly typical problem, right? So we have a pendulum, right? And then the bullet hits it, and then it's just an inelastic collision. So we just write m1 v0 is equal to m1 plus m2 times v prime. And then at the very top, we want the centripetal acceleration to be mg, basically. So we have 1/2 mv prime squared is equal to 1/2 times, wait up, let's draw this. So it's L here, so the height change is 2L, so 1/2 mv2 squared plus mg2L. And then the last equation we want is that mv2 squared over L is equal to mg. Okay, so we have a bunch of equations, now we just gotta solve them. Alright, so we have v2 squared is just equal to gl, and we can cancel out all the m's over here. So basically we have 1/2 v prime squared is equal to 1/2 gl plus 2gl. So we basically have that v prime squared is just equal to 5gl. Okay? And then we could plug that into our original equation, right? m1 v0 is equal to m1 plus m2 times 5gl. And then we just divide by m1 to get v0, and is that the answer? Oh wait, root 5gl. Okay, and that is just answer E. Epic. So 22 is E. Alright, 23. Consider two uniform spherical planets of equal density but unequal radius. Which of the following is the same for both planets? So escape velocity from the planet's surface. How much time? Okay, we're kind of a bit close. Okay. So escape velocity, is that gonna work? So basically escape velocity is just equal to negative gmm over r. But in the case where you have more r, then you have more mass, and you also have more r. But mass increases with the cube of radius, not with the single of radius. So escape velocity is going to be different because mass increases faster than radius does, so it changes. We also know that acceleration due to gravity is just gm over r squared, but we also know that m is going to increase with r cubed, so that also depends on r, so it changes with r. And then orbital period of satellite in circular orbit just above the planet's surface. Alright, let's see. So basically, to find the period, your period is basically going to be 2 pi r over v, but you can find v using the equation v squared over r is equal to gm over r squared. Okay, so if we multiply by r here, so we can replace m with r cubed, right? That just makes it simpler to understand. So this is r cubed basically, k times r cubed, but it doesn't matter. V is equal to root g over r squared. And then if we plug it back into the original equation, then we get that, v equals root gr squared, and then we get 2 pi r over root gr, and then the r's cancel out. We found the r's cancel out, so it doesn't matter on r. So that means it has to be the same for both planets. Okay, it's just C. Epic. Okay, 24. Upward from the ground. A ball is launched upward from the ground at initial vertical speed of v0 and begins bouncing vertically. Every time it rebounds, it loses a proportion of its magnitude of its velocity due to the inelastic nature of its collision, such that the speed just before hitting the bounce is v, then the speed after is rv. Okay? Calculate the total length of time that the ball remains bouncing, assuming any time associated with the actual contact of the ball is negligible. So it starts from the ground and goes upward, and then it has another one, so it's basically this. Boom, 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 boom. Okay. So the equation for the time spent in the air, you could just derive it from this. So we know that it starts with v0 here, but it ends with v0 on the way down. So we know its acceleration too, so we basically have that v0 minus gt is equal to negative v0. And then t is just equal to 2v0 over g. So basically, the next time it's going to be rv0, and then the next time it's going to be r squared v0, and then it's just going to keep multiplying by r every time. So this is like a geometric sequence. So we have 2v0g times 1 plus r squared plus r cubed plus dot dot dot. And then this is just an infinite sequence, so it would just be 2v0 over g times 1 over 1 minus r, which is a. Okay. And last question, and then we'll go back to 21. We didn't do that yet. Alrighty, two satellites are launched at a distance r from a planet of negligible radius. Both satellites are launched in the tangential direction. The first satellite launches correctly at a speed v0 and enters a circular orbit. The second satellite, however, is launched at a speed of 1/2 v0. What is the minimum distance between the second satellite and the planet over the course of its orbit? So basically, in a circular orbit, the kinetic energy is equal to the gravitational potential. Or rather, its overall energy is like 0. So the equation for this is 1/2 mv squared is equal to gmm over r. Where capital M is the mass of the Earth, and then lowercase m is the mass of the satellite. So basically, our total energy is equal to 1/2 mv squared minus gmm over r. So in this case, in the circular case, this is 0. So we have this equation, right? But if we 1/2 our velocity, then we have to 1/4 this. So 1/2 mv prime squared is gmm over 4r. So in the second case, we have that our energy is gmm over 4r minus gmm over r, which is equal to negative 3/4 gmm over r. I actually don't know exactly how to do this, huh? There was a formula for this, but I forgot. How much time? Let's see. Okay, 10 minutes. This is actually kind of hard. What is the equation for it? Okay, we could use two equations. So first, we know that angular momentum is conserved. Okay, so we have mv0 m times 1/2 v0 r is equal to mv prime r prime. And then our energy is also constant, so 3/4 gmm over r is equal to 1/2 mv prime squared minus gmm over r prime. So basically from the first equation, we get that v and r are inversely proportional. And then from this one, we have to do some fancy stuff. So we get that from this one that v prime over v0 is equal to 2r prime over r0. And then, what could we do? If we plug it into this, okay, this is gonna get kind of nasty, but we gotta do it. Alright, so negative 3/4 gmm over r is equal to 1/2. Alright, I'll just write this out. Let's hope it works out. I don't know. Alright. Let's go back to 21. Didn't think that would be more worth our time. Let's see. Alright, 21, let's see. Given the total kinetic energy of the system and the mass of each dotted particle, it is possible to determine the speed of each dotted particle. I highly doubt, I'm pretty sure that that's the answer. Because if you have the three system, you have two equations, right? You have conservation of energy and you have conservation of momentum, but you still have three unknowns, the velocities, and only two equations, so there's no way to solve for that. So I think we're good. B for 21. Alright, what are we gonna guess for 25? I don't think I can solve it in the time we have, so let us just go with, let's go with C. How about C? C looks epic. Okay, I know I have 4 minutes left, but we're just gonna check our answers. Let's see. Let's do this. Okay, so go back, we go to 2008 solutions, and let's check. Alright, D, C, A, D, C, A, C, B, B, A, D, B, 14. We got 14 wrong? How did we get 14 wrong, bruh? Okay, 15, D, E, C, B, D, B, E, C, A. Aw, we didn't guess 25 right. Rip. Hey, 23 is not bad. 23 is pretty good. But let us see where we messed up. What the heck? How do we miss number 14? Alright, 14, where are you? Okay. So I said the answer was 4E. Okay, let me just do it real quick and then see where we went wrong. Oh, wait. Did I just like circle the wrong thing? Because, oh, I must have done like 4 over 2 is equal to like 4 or something. Okay, so that was a silly mistake. So 14 is B. Pretty epic. Alright. Hope you guys enjoyed that. I have no idea how to solve number 25 off the top of my head. I'll probably have to like look it up a little bit, but that's pretty good. Pretty good, pretty good. Alrighty, hope you guys enjoyed that. One of you guys suggested it, and I think it's a pretty good idea. I think just showing you guys how I approach a problem and how like I jump around and like skip problems, and how ultimately you can get a 23 on FMA. So, hey, generally speaking, like you want to have more time to check your answers because each point is extremely important in FMA. So don't be like me and like talk to your camera while you're doing it. But hey, it's still pretty good. Alright, thank you guys for watching. As always, if you enjoyed the video, leave a like and subscribe for more. Thank you guys for watching again so much, and see you guys next time.